Welcome. This is Richard Pickings at Bridgeside Software. In this tutorial, I'll discuss what to do when PGSuper's design algorithm fails to come up with a usable design. And I'll also include a discussion on Haunch design. In this example, I'll use our PGSuper Professional program to design a TxDOT I-girder bridge. But the basic concepts apply to all versions of PGSuper and any type of girder for any agency. Here's the BridgeLink start screen when you first open the program. PGSuper's already been configured to use the TxDOT specifications and standards. And if you want to know how to configure PGSuper for a DOT, you can look at some of our earlier beginning videos. So we're going to start with a TX54 template. So we'll go to File, New, select PGSuper Project Templates, I-girders, and this is the TX54 beam, which is a template set up by TxDOT. This is a commonly used section in Texas. You can enter project properties if you want. All highway agencies in the U.S. use the AASHTO LRFD bridge design specifications, but most also have their own design manual with deviations from LRFD. PGSuper has an amazing amount of design options, which allow it to be customized for most DOTs. So now let's take a look at the TxDOT configuration and their settings, a few of their settings. So here I'll go to Library, Edit Libraries, and select Project Criteria. One thing to notice here are the little locks and checks in here. The lock means that this is a master library from the TxDOT, and you'll not be able to edit this entry. The check indicates that this is the current project criteria for our project. Most of the settings can be found in the project criteria library, although there are other important settings in the girder library and also in project templates. And I'm only going to have time today to discuss a few settings, but as an engineer, you should be familiar with your agency's specifications and PGSuper's settings for them. So here we are on the General tab, and from this tab, you can set which version of the AASHTO LRFD you'd like to base the specification on. We're going to look at a few tabs here. Let's first look at spec checking and design. These are all the design and checking, not all of the design and checking options, but many of them in PGSuper. And as you can see, a lot of things are not checked or designed for, and this is chosen by the Texas Department of Transportation. Some of the main things I'd like to point out here is they do not check for lifting stability or hauling stability. They leave this up to their precasters. Another thing you might take a look at here is the add strands using permanent fill order. We'll talk a little bit about that later. And designing the haunch geometry. There's some settings here, how to round up and tolerances that the design needs to be within to pass the spec check. Next, I'll take a look at creep, camber, and haunch, since we're going to discuss that later today. And this allows you to select what option in the camber and haunch input you want to use and how the camber in the program, input into the program, is going to be utilized. So here we can see that the haunch dead load is computed using the detailed haunch design. This means you have a non-prismatic haunch line along the girder. And here it's, as you might notice, for stiffness and section properties, they ignore the haunch depth. they assume that the slab is directly on top of the beam for section property calculations. Last, let's look at the limits and warnings tab. And I just want to focus on two items here. For normal weight concrete, our max allowable release strength is 6 KSI, and our max allowable final concrete strength is 8.5 KSI. Time to edit the bridge. I want a one-span bridge with a slight skew, so I'm going to go ahead and delete Pier 2. Then I'll change the span length to 132 feet. And we want a skew here, so I'll go ahead and do this from Edit, Bridge, select the Layout tab, and I want to orient both piers in the same direction, so I'll use this shortcut here, Orient Piers, and say 30 degrees right. This is our simple final bridge layout. Now I want to take a look at the Haunch geometry design. Let's look what Texas pre-inputs in their template. So I'll go to Edit, Haunch, and from here we can see the Haunch geometry editing dialog. At the top of the dialog is the fillet. Think of the fillet as the minimum allowable haunch depth at any location along the girder. The fillet serves as a buffer that prevents the girder from intruding into the deck in case camber in the field is larger than predicted. Texas uses the A and assumed camber method for defining the haunch in PGSuper. A is also known as the slab offset, or X dimension in Texas nomenclature. This figure describes this case. The slab offset is the depth of the slab plus the haunch depth as measured at centerline bearing and centerline girder. For input purposes, haunch depth is always measured along the centerline girder. Assumed excess camber is a user input value that defines total mid-span girder camber at final. For this type of input, camber is assumed to vary parabolically between the bearings. PGSuper checks that the assumed input camber is equal to the computed camber within a tolerance as defined in the project criteria library we just saw. And a spec check failure will occur if this comparison lies out of tolerance. Here we can see that the slab offset was input as 10.5 inches in the template. And up here in the right corner, it shows us that our depth of our deck is 8.5 inches. This means that the haunch depth at centerline bearing is 10.5 minus 8.5 equals 2 inches. The assumed excess camber is set to 1.5 inches. This means that we're assuming that the camber at midspan is 1.5 inches, which gives us 2 inches minus 1.5 inches equals a 1/2 inch, which is a 1/2 inch haunch depth at midspan. Note that this exactly meets the fillet depth at midspan if we have a flat vertical profile and 0 super elevations. I'm going to input a value of 1 inch for assumed excess camber to give us a little more wiggle room. Before we design girders, let's take a quick look at how PGSuper's flexural design algorithm fills strand locations. We'll go to the girder library entry. So I'll go to Library, Edit Libraries, go here to the girder library, and let's take a look at our TX54 entry with the red check, which means it's being the current girder used. I'll double click, which brings up the library entry, And I'm going to go to the Permanent Strands tab. There's multiple places in the library entry where you can view the cross-section of the strand, and I'm going to view at mid-girder. So here in this section view, you can see it displays the section properties of the girder, and it also shows all of the available fill locations for strands. And as you can see here, the strands are filled from center line out and bottom up. This is prescribed by the Texas DOT, but if your agency doesn't prescribe how to fill strands, this is a good way to go. So this means if you have 20 strands in the girder, it's going to fill this bottom row and then up to 19 and 20 here. As you can see, all of the girders in our make-believe bridge are the same length. When this is the case, you should strive to make all of the girders identical for ease of manufacturing and construction. But we know that dead loads and live load distribution are unique for each girder, so we need to determine the controlling girder. An experienced engineer can often determine this from examination, but another method is to simply run the design algorithm on all girders in a span. To simplify our discussion, I'll only run the algorithm on girders A and C. So we go to Project, Design Girder. We want to design multiple girders, and I'll select A and C. We want to design for flexure, design the haunch geometry, and design for minimum concrete strength. Also, we don't want to design for shear because TxDOT has their own special detailing for stirrups. The structural design algorithm makes a highly educated guess at an optimal design. I say guess because it may not always converge on what you consider to be optimal. Finding a design is a nonlinear process. At the highest level, the design algorithm uses a multi-level Newton's method iterations to attempt to converge on an optimal strand layout for the lowest possible concrete strength. The process is simplified for TxDOT design since they do not consider girder lifting and hauling. To learn more about the algorithm, check out links on the page at PGSuper.com where you found this video. The papers authored by Richard Bryce at WashDOT describe and provide flowcharts and detailed example calculations for the complete design algorithm, which considers all fabrication options, including girder lifting and hauling. I encourage all engineers who use PGSuper to check this out. Both designs were successful. This is good news. We should be able to work with this as a starting point once we've determined the controlling girder. So let's look at the design summary. As we can see here, girder A required 48 strands and girder C required 50. Perhaps more importantly, we can look at the concrete strengths, and we'll see that the release strength for both girders exceeded the maximum release strength we found in the project criteria. This is going to be a problem. But from this we can see that girder C is our controlling girder, requiring both more strands and higher concrete strength. I'll scroll down to the details of girder C. Again, we've exceeded the max normal value of 6 KSI, which is unacceptable. So here's an example of design that works, but it's not acceptable for our needs because of the high required release strength. So at this point, we could choose a larger girder. But our fake bridge is crossing a fake railway, and a deeper girder would cause clearance problems. So we need to work with what we have. Taking a look at the slab offset just quickly, we can see that the design algorithm modified the required slab offset and assumed excess camber. this is okay. So we're going to use the haunch geometry from span 1 girder C, and we're going to apply it to the entire bridge. So I'll go ahead and accept the design. Now let's focus on girder C, which is our controlling girder. In PGSuper, you should always run a spec check after a design. So I'll go ahead and do this by right-clicking on the girder and selecting spec check report. I'll use the table of contents to go to the specification check summary by right-clicking on the report. As we go down here, we can see that our specification check was successful. This means the current design will work as we want. But if we look down here in the status bar, you'll notice the yellow 2. By double-click on it, the status center is telling us that our concrete strength is exceeding our normal value of 6 KSI. So we're going to want to change this. I'll go ahead and edit the girder by clicking up here on Edit Girder. Since girder C is selected, it jumps right to the girder C dialog. And I'll go ahead and change the release strength to 6 KSI, which is our maximum allowed by TxDOT. And I'll go ahead and click OK. Let me go back to the spec check summary. And here we are. It's telling us that our specification check was not successful. We're failing in compression stress at the release interval. Another way to run a spec check, and especially if you're in Texas, is to run the TxDOT summary report. I prefer the long form. And this will give us the same information. We can go to table of contents, specification check summary. And one way to find the failure is to use the find feature in reports. So I right-clicked, I can click find, and I'll click on fail. And this will take us a couple of clicks down until we see right here is our failure for service 1 compression at release. We can see that this is near the end of the girder. Another way to look at this is to bring up a graph. So I'll go to graph analysis results. Since we're at release, it's before erection. I'll go to stress, and we'll take a look at service 1, demand, and limit. And as we can see right here, this is our failure. Our failure is at the ends of the girder, and it's in compression, and it's at the bottom of the girder. What usually causes this is we have too much pre-stressing force at the bottom of the girder. That causes this compression. So what can we do about this? We could increase concrete strength, but we've already done that as much as possible. And another option then would be to reduce the number of strands. Let's take a quick look at our girder. We can see that this girder is pretty loaded up with strands. I can move the section cut here and look at the end of the girder. The strands are harped. Well, let's take a look here. Let's see. We have a really cool tool in PGSuper Professional called the Girder Design Dashboard. This gives you a view of multiple different limit states. So what we can see here for all stress limit states is our failure right here. This is our compression at release. And what I want to take a look at here is our service 3 tension at final. And kind of zooming in here on this graph, we can see that we're pretty maxed out here. Demand is close to being equal to capacity. So I don't think we're going to be able to decrease the number of strands in the girder. That's not an option. So let's look at some other options. I'm going to go ahead and close this. and go to Edit Girder. And one shortcut here on these graphs is you can double click and right there, and it will bring up the editing dialog for the girder that the graph is showing. I'm going to go here to the Strands tab. One of the things you want to look at the very first whenever you run a design is, did the design algorithm max out harping at the end of the girder? And what we can see here, we have 48.5 inches, and the upper limit is 50.5 inches distance between the topmost strand and the girder bottom. So it did not harp as much as possible. So I'm going to try to increase the harping. Now I'm going to change this to 50.5 and see if that makes any difference. If you look closely at the graph, you'll see that it made a small difference, but it didn't get us quite to where we want to be. And it kind of as a last resort here, we're going to have to swap straight strands for harp strands. So again, I'll double click here, go to the Strands tab, and what I want to do is change the strand definition type. Typically for TxDOT, you define strands just purely by the number of strands, as we've spoken of before. So we have to change this setting so we can adjust straight and harp strands separately. I'll click here, and this allows us to change number in straight and harped independently. And what this will result in is a non-standard design in TxDOT nomenclature. We'll talk a little about that later. So I'll reduce the number of straight strands to 40, and I'll increase the number of harp strands to 10. And let's rerun this. Now, if we go back to our spec check report, we'll see that our design was successful. Well, that was pretty easy. We can now copy this design to all of the other girders in the bridge. So let's go ahead and do that. I'm going to go up here to Edit, Copy Girder Properties, and I want to copy from our controlling girder C that we've been designing to all spans and all girders in the bridge, and I'm copying all girder properties. I'll click on Copy Now, and we can see now that all of the girders are the same. I'll go ahead and close this, and now we want to look at spec checks for all girders in our bridge. So I'll go up here to the multi-girder spec check summary report. This gives us a quick view of all of the girders in the bridge. Okay, here's our spec check summary. I'll go ahead and scroll down, and we find here that we have succeeded. All of the girders in the bridge now pass the spec checks, and they're all identical. So now I think we could just go home. Oh, wait. Oh, no. Our roadway designer just told us we messed up. There's no drainage on this bridge. How could we have missed that? Let's take a look. Oh, no. The bridge is flat. Okay, we have to make a last-minute geometry change here. So I'll go ahead and edit the alignment. Go to the roadway cross sections, and our roadway guy told us that we have a 2% slope going off the center line of the bridge. So I'll go ahead and enter that. Let's see what the change in super elevation does to our multi-girder spec check. Oh no, now our design fails. Looks like the exterior girders have a specification check failure for slab offset. What could be causing this problem? How would a change in super elevation affect haunch design? Let's take a look at this figure. Figure is for a U-beam, but it's also applicable to our I-beam design, and it shows what the problem is a little better. As you can see, we have a plumb girder with a sloped roadway. The outer edge of the girder on the low side of the slope has a smaller haunch, and this is where the fillet check occurs along a girder, is the least haunch along the girder. So our super elevation has caused us a slab offset problem. The best way to look at haunch problems when you're looking at the entire bridge is to look at the multi-girder haunch geometry summary. I'll scroll down and we can look at the failure. So we've input 11 inches for the slab offset, and now the program is telling us that we need 11.5 inches at our exterior girders. We'd like to keep the slab offset the same along the entire bridge if possible. So let's go ahead and change our slab offsets to 11.5 inches along the entire bridge. Our slab offset checks now pass. That's a good thing, but let's go back to our multi-girder spec check summary and see what's happened. Oh no. Now it appears that we've increased our haunch depth, and this has caused more dead load and is causing our service 3 limit state tension at final to fail. Oh, we have some work to do here. Let's take a look at our controlling girder again, girder C. So I'll go ahead and close the multi-girder checks for now. And let's run the girder design dashboard just to see what's going on in this girder. And as we can see, for all stress limit states, everything passes except for service 3 tension. I'm going to go ahead and bring up a spec check report for this girder only. And here we are. We look at the summary. Here's service 3 limit state. So I'll use the table of contents to go down and look at this in detail. And what we see, we have a capacity demand ratio of 0.96, and the concrete strength required to satisfy this requirement is about 8.7 KSI. This is higher than the 8.5 KSI that we can go to for a Texas design. So we're in a bit of trouble here. Let's give it a try. Let's change our concrete strength in this girder all the way to 8.5. So I'll go ahead and go up here to Edit Girder and change to 8.5 KSI. This will get us a little way toward solving our problem. Here we are back at our check, and we can see now that we've gotten pretty close. I'll increase the size of this window. Now we're at 0.99 capacity demand ratio. We're not too far from the problem. Quickly looking at the design dashboard again, we can see that we're almost there. I'll try adding a couple of harp strands. This should increase the pre-stress force at midspan while not causing end zone changes. Oh, look at that. It looks like our spec check may have passed. I'll go back to the spec check report for girder C, table of contents, go to the summary, and now we have a passing design for girder C. Again, we need to copy this design. We'd like to have the same design for all girders in the bridge. So we'll go back to the copy girder properties, copy from girder C to all girders, and see if maybe we've fixed the problem. Go ahead and go back to the multi-girder spec check. Select all girders. Now we can see we have a spec check summary with specification checks for all girders in the bridge successful. This is great. It looks like we have a good design here. But there's one last check we should always make. The AASHTO manual for bridge evaluation and the AASHTO LRFD specifications are highly correlated. But there are times when you can have rating factors less than 1 and still have a successful LRFD design. So let's make sure our rating factors are going to rate. To do this, I can go to the TxDOT summary report long form and select load rating summary at the bottom. I'll just go to the bottom of this report and we can see that it's load rated girder C, or controlling girder, and we have all rating factors greater than 1. So this is good to go. There's another way to check all girders in the bridge, and we can go to the load rating summary report here, select by individual selected girders. I'll select all, and I just want to see the load rating. So I'll just select the first chapter in the report. I'll scroll down, and here it tells us that the rating factors for all of the girders are greater than 1. One thing interesting here is the load rating controlled for girder E. This isn't a girder that we used for our initial design, and this probably was the controlling girder. I guess it is smart to select all girders at the beginning for design to find out which girder controls. I also encourage you to run a secondary software program or hand calcs to check your design. One last note about our design here. As you recall, I made a last-minute change to super elevations, and it almost derailed our girder design. So I think it's really important to know that you should input accurate bridge geometry unless you're just doing a very preliminary design. Otherwise, you may run into trouble like we did. And luckily, we were able to get the girder to work in all locations. Now, if you're from TxDOT, the last thing you want to do with a design here, final thing, is export to a Texas CAD data report. We do this from File, Export, as shown here. I'll select all girders. I can select the girder design table or the haunch and deflection data. For now, I'll just use the girder design table. And this will export our results into a Excel spreadsheet that's ready to go into Texas standard plans. So let's take a look at our spreadsheet here. As you can see, we have page 1 and we have a non-standard strand pattern that PGSuper has exported the strand arrangement. This would be your final step in a TxDOT design. Okay, that's all I have for you in this tutorial. This is Richard Pickings from Bridgeside Software, wishing you happy bridge designing.